Yes, doctor, because some students asked.
Can you see my snipping tools tab?
Yeah, yes. Now everything is clear. Yes.
Okay, thank you. Okay, again, when we talk about power electronics, so power electronics means that we are going to learn about power processor. Means that from the source, maybe it come in AC or DC whatsoever source, before we supply to the load, so we have to process in terms of voltage, current, power before we deliver up to the requirement of this load. And this load, it needs maybe low voltage, maybe it needs higher frequency, maybe it needs some sort of process kind of power. So we have to suit it with our power processor module. So when you learn about rectifiers, so it means that we are converting from AC to DC. And so this is the first part that we're going to discuss about rectifiers or AC to DC power processing. Okay, later maybe we talk about from previously we have AC to AC, and maybe we have AC, DC to AC. So now this is DC to AC. DC to AC inverter. Maybe from DC to DC, which is maybe we have some certain level of DC, but the load need only a certain level of DC, so we have to process the voltage or the power to suit the requirement of our load. Okay. Out of this chapter, which is AC to DC, which is rectifier, what we expect you all to understand is that you understand to how the operation of the rectifiers, and in the circuit, how the rectifiers operate or behave, and to understand the performance parameters of the rectifiers. Later on, you will see we have a source, AC source, we have rectifier. Before we deliver to our load, assume as pure resistor. So this is our rectifier, diode. Maybe we have some sort of other rectifiers. Okay, how the operation of this circuit and how the performance of the diode itself. Then how to analyze the circuit and what you expect to get from this output. So how to analyze the output, how you want to determine the voltage level of the output here. Then to learn how, in terms of the techniques of design the whole circuit here. How you want, what you need to consider in terms of designing the entire circuit of this rectifier module. Okay, this is your source, this is your load, this is your device. The whole of these three items considered as your system. Okay, so that is what we expect you all to understand throughout this chapter. Okay, next we go to the next slide. If you have any answer, or
we can't see your slide right now. We can't see your. We cannot see your slide right now.
I just off. Okay.
I see. Okay.
Okay, I just off, and because I try to proceed with Microsoft 360, but still in the process, so I have to present throughout this snip. So it's quite a hiccup process lah. So we proceed one by one with snipping tools for today lah. Sorry for the hiccup. So you can jot down on your slide, on your notes lah. I'm presenting through snipping tool. You can jot down on your slide, on your handouts. You can see my snipping tools tab?
Yes.
Page
yes.
now? Okay, thank you.
Yes.
Okay, as I mentioned before, AC to DC converters is a circuit used to convert from AC to DC, which is also known as rectifier. Okay, we have other kind of modules as well. If we convert AC to DC, it's so-called rectifier. If AC to AC, the name is AC voltage controller, or we call it before a cycloconverter. We have this syllabus previously in our chapter, in our subject, but already been taken out for this semester because this cycloconverter is seldomly used right now in the industry. So we have replaced with the inverter instead. Previously, we don't learn inverter in Power Electronic 1. Maybe we learn in Power Electronic 2 or other subject. But we have replaced with this cycloconverter with the inverter. Okay, so you will see that this chapter of DC to AC, also called inverter, is going to be learned and discussed within this semester. If you refer to previous exam question, there will be no answer question for inverter, but this semester upwards, so you will have inverter discussed in our subject. And we have DC to DC converter, or we call chopper and chopper. Okay, on the next slide, you can see the types of rectifier. It's stated over there: half-wave rectifier, full-wave rectifier, uncontrolled rectifier, controlled rectifier, single-phase and three-phase rectifier. So what does it mean by half-wave and full-wave rectifier?
Half-wave only one diode, and full-wave, that's mean you have to use two diode, right?
Yeah, means that it will process both sides of your signal. Positive and negative will be filtered or will be processed. If half-wave means that only positive part or negative part is processed, meanwhile another part will be voided. Okay, what does it mean by control and uncontrolled switch?
Like dynamic? Dynamic range?
The slide first. We move to the next slide. Sorry. One minute. One second, please. Okay, half-wave means that if you have a AC, so you will have only one diode before it goes to your load. Is that it will process. You have here the input of full wave, but you will see that only half wave of your process signal. It rectifies, then it blocks. It rectifies, then it blocks. Rectifies and it blocks. And even though you pump in the full wave of signal, only half wave is processed. Meanwhile, if full wave rectifier, so you have AC source, you will have more than one component of diodes here to compose as your full wave rectifier. So actually the connection will be here. Come here, it goes to here.
I think, Doctor, also we can use center tabbed, right?
Come again?
We can use center tabbed rectifier.
And yeah.
Or bridge.
Almost the same. But this one is for rectifier. Means that on the positive side, it goes here and it goes to the diode. On negative cycle, it goes here and also it go into the diode on the positive side. So
I think I think this one is clipper, right? Clipper.
This one is rectifier.
I see.
This one is clipper. This is uncontrolled module. Means that you cannot control the diode. Once it's turned on, it's turned on. It will turn off only on the reverse bias. On the positive bias, it will conduct. But on the negative bias, it will block. So positive bias, it conducts. Negative bias, it will block. Positive, it conducts. Negative, it blocks. Okay. So this is half wave rectifier. Meanwhile, this one is a full wave rectifier. So it will be a big difference in terms of number of components. And once it involves multiple of components, it involves cost. So that's why we need to consider in terms of the what so-called to justify, are we going to proceed with this kind of circuit if you are an engineer for a certain company, or are you going to proceed with this kind of circuit to sell to the market? So it's up to your justification.
Doctor, actually, I have a question.
Yeah, come again. Louder, please.
Actually, for the second diagram that you used, I think the diode must be serious with the load. If you put the diode parallel with the load, it's gonna be clipper, right?
Put it parallel with the load.
The diode must be serious with the load. The signal never can be like this if you put the diode parallel with the load. This one we call it clipper. You will mind, right?
This one is rectifier. Maybe some in some books called clipper.
But if you put the diode, if you put the diode parallel with the load, the equation gonna be V bias plus 0.7. So the signal, it's never gonna be like this. The diode must be serious with the load, doctor, if I'm not mistaken.
Diode series with the load. This is series with the load. This one is it. If you refer to the books, so this is the composition. Maybe we discuss later on the clipper point of view that you said. Okay, we proceed with this one first, because maybe the clipper will be touched in this kind of control parts. Okay. So this is the composition of half wave rectifier. Meanwhile, this one is a full wave rectifier. You can refer to the notes later. Okay, what about uncontrolled rectifier? And uncontrolled rectifier also refer to the switch. Means that we cannot control in terms of when to start or when to stop the conduction. Okay, it conducts when the current cross the zero level, move to the positive part. So it only stop when it cross another zero going to the negative side of oscillation. Okay, it's uncontrolled. But when you see some device with this kind of marking, so this is so-called diode. But when you see some sort of this marking, so it means that you have some sort of signal that will be induced to the part. So this kind of part is so-called a control device or control switch. And if without this part, is so-called uncontrolled switch. So if you put the uncontrolled switch into the circuit, so it will become uncontrolled rectifier. If you put a controllable switch into the circuit, it will be called as control rectifier. So how to control, we'll discuss later, because different device, they need different kind of control signal. Okay, what we means by single phase rectifier. So this is the single source, single phase. So this is single phase rectifier. What about three phase rectifier? A three phase rectifier is a rectifier that rectifies the three phase of our source. We have phase A, phase B, phase C going into one system, so we shall have a three phase rectifier. Okay, this is for single phase. If you have composed from three different source of phase A, B, C, or red, yellow, blue, so it comes into your module, it goes into your load. So this is so-called three phase rectifier. Okay. Okay, next slide. You can see the composition of the circuit over there.
Tak nampak je. Tak nampak.
Tak nampak? Okay, wait. Okay, inside your printout slide itself, we have a composition of the circuit. So what per I draw just now is this kind of circuit. Just that it draw over here in terms of diamond kind of drawing. You can see.
This is a bridge, right?
Wait, one moment, please. Okay, you have any question? The drawing that I draw just now is just like this one. It's just that the arrangement of your diode here, D1, D2, 3, 4 here it's arranged in diamond type. What I draw just now is this kind of arrangement. Just the same. If you can imagine or visualize this in this kind of arrangement proper, so you can draw or you can visualize in this kind of drawing. But if you prefer with this kind of drawing, so it's up to you. You can draw in this kind of drawing. Okay, for the uncontrolled half-wave rectifier, we assume a simple resistive load. During positive half cycle of the input voltage, the diode here will conduct and the output appears across the load. So as I explained just now, when on the positive cycle, so you shall have a positive cycle here. But when it circulate or it turns into the negative cycle, and first the current flows from anode to cathode and from left to the right, so it flows. So you can see the output. But when it flows from front here, right to the left, so the diode will block the flow of current. So there will be no negative half cycles. So the output voltage is 0. Okay, this is the, you have to take note that when you simulate or when you measure on the scope and you use multimeter or when you use a measuring device, it will measures, it's up to your options. It will measure sometimes average, as what you have performed inside your lab 1. Sometimes it measures RMS, sometimes it measures peak. So it's up to you and depends on the type of circuit that we are facing or we are dealing with, which values or which attributes units are preferable or correct to represent our measured signals. So if you probe or you simulate through a scope, you shall see that the output that appear on the scope or on the simulation is peak value. So VM here represent the peak value. So let's say if you want to present in terms of RMS, so we have to divide by 2. Okay, here Vs is the RMS value equal to V peak sine omega t. So this is V peak, this is RMS. Okay, so what you can see from your scope or your simulation is the peak value, instantaneous value. Okay, this is instantaneous value lah. At 0, t equal to 0, so the output is 0 lah. When it reach pi divided by 2 and 90 degree, so it reach peak value. And so this is your instantaneous value, this is your peak value here. Meanwhile, the overall Vm sine omega t is your RMS value. Okay. Okay, this is the peak value of your input voltage. Meanwhile, this is your observed value output at V out here. What you measure from here, if you put a probe, so this is the signal that you will see. For the half positive cycles, you start to ramp up, then go down on the half cycles. 2 pi is 1 full cycle. So pi here is your half cycle. Ramp up and disappear here. Because when it enter the negative cycles, the diode will block the voltage. And you block the voltage, the current will not flow. So it flows positive, it blocks the negative. But when you measure on the diode itself, and you can see that during positive cycles, the voltage drop across the diode is 0 because it allows current to flow. So the voltage drop is 0. But when the negative cycles appear or negative cycles happen, so it blocks. So it will block from the right to the left here. So you will see that the voltage will appear on the diode itself, ramp up on the negative cycles up to the negative V peak and go down to 0. So ZApier happens continuously for this uncontrolled half wave rectifier. So this is the R load. So if this is the plot for voltage, what about the plot of current? So how the current looks like actually? So for your information, if we have we are going to plot the current. Sorry. If we are going to plot the current, so for R load, resistive load, the phase of your, let's say this is your input. So they'll be at the same phase. And this is your input. So this is V out. The current also will follow the same pattern, which is here. Once you have a flowing voltage throughout the diode and also throughout your load. So the current also will ramp up. And it blocks here, it's ramp up, and it's blocked here. Okay. Same goes to here. We can measure the current as well, because whatever flows, sorry, there is no current. On the reverse bias, there will be no current because it blocks. Okay. There will be only current that flows on the positive cycles. Later, when we analyze in terms of RL load, this is only R, but if R plus L, there will be a shifting of current of theta. Okay. Next, so the output voltage on average, and the average output voltage here, it's not the RMS, average output voltage. So you have to take a look, be alert, because sometimes we measure average, sometimes we measure peak, sometimes we measure RMS. So you have to be alert on that. Okay, the output, which is the average value, because we are dealing with rectifier now. V out is considered as the output, the average value of the output, which is, if you calculate in mathematics values, is equal to 1 over full cycles of 2 pi here. Integrate between 0 to pi, because we only have half cycles. Sine omega t d omega t. So if we solve the equation, it will be only V peak divided by pi. So that's the average output of our signal for half wave rectifier. Meanwhile, in terms of average current, how much the average current will be also the same. Average voltage that we calculate divided by value of R. So this is the Ohm's law, V equal to IR. So I equal to V over R. Meanwhile, your V out is Vm over pi. So you put in Vm over pi here, times 1 over R. So it become Vm over pi R. So this is the average current. What are average power absorbed by the resistor? So P is equal to IR, I square R, sorry. This is power equation. P equal to I square R, P equal to V square over R, or P equal to VI. Wait. So this is your average. This is your average as well. So this is your peak. So this is your Ohm's law, V equal to IR. So if you want to find I, so it's equal to V over R. So V is your, this is your I naught, so this is your V naught. Or you have to insert the initial values just now, which is Vm over pi times 1 over R. So it becomes Vm over pi R. Okay, meanwhile your power equation is P equal to Vi, P equal to I square R, P equals to V square over R. So depends on which place or which event you want to use. Usually this one we use for losses. How to calculate losses? This one is the power, output or consume power. This one is the power losses on the certain device. So the power absorbed by the resistor, how much absorbed by resistor? If we acknowledge or we know how much the current that flows through that resistor, how much the current flows, so we can use, we know the value of R, we know how much the current that flows through, so you can use I square R. Or we know how much the voltage drop through the resistor, and so we can use V square over R. And so it's up to the condition and situation where and what kind of data that available at that time. So this is the power equation that you are able to select and use. Okay, but in terms of RMS, VRMS is equal to VM just now, divided by 2 for this half wave rectifier. So IRMS is equal to VM over to R, and I is, you include again the Ohm's equation here to the equation, so you get the absorbed power of the resistor. So absorbed power resistor, you have to bear in mind that the value is to be RMS and RMS. If you go to the example, so sorry. Stated there for half wave rectifier circuit, the source is sinusoidal, 240 volt, frequency of 50 Hz. So bear in mind that when we talk about half wave rectifier, so it does not also called effect by how much the frequency is so far. So stated here RMS, and so V in is 240 volt RMS. Meanwhile, your load is 5 ohm. The load resistor is 5 ohm. So determine the average load current. So what is your I out and load current? How much is your I out? So you start with the I out is equal to V out divided by R. V out divided by R. But your V out is V average, which is equal to 1 over 2 pi plus 1 over 2 pi of the equations, but it's end up be the Vm over pi. V out is your V average, which is Vm over pi. So you put in your Vm over pi here. So I out will become Vm over
by R.
by R. So this is your I out. So VM, this is VRMS. Okay. So you have to times cert2. Cert2 times 240 volt RMS divided by pi 5. So you will get how much? Your I out. 21.6, is it?
Equal 18.
Yeah. So cert2 240 divided by pi. So this pi is 3.142. And so you have to ensure that if your calculator set to correct unit, so it should be 31.142 lah. And if I'm not mistaken, this is in radian. Okay, we become to 21.6. So this is the average load current. What about the average power absorbed by the load? So this is your A. So average power. How much is your average power? So P average is equal to I square R. And so you have your I. So this is your I. Your times your R. Or you can divide, you can get your, calculate your VRMS here, divide by R. Also can. So P average is equal to I square R, or equal to V square divided by R. So you can use any values. So let's say if you want to find from IRMS, so IRMS 21.6 squared times 5, 2332.8. Wait, I want to check again the answers here. Sorry guys. Okay. This is your average. Okay. This is IOUT average. It's not RMS values. So you cannot use directly this 21.6 ampere here. You have to get the average power. You have to convert from average into RMS. Okay. So IRMS is equal to V RMS divided by R, or VM divided by 2R. So if you're taking this one, so your IRMS is equal to VM divided by 2R. So your Vmax is 2240, which is 340 divided by 5. How much you get?
Uh, 21.6.
21.6 your average.
I think Sarah didn't put the by.
Come again.
340 divided by times 5.
Divide by 5.
Divide by times 5.
Divide by pi.
Times 5, yes.
So you get
21.64.
This is the output current. Okay, let's say we are taking a V out RMS divided by 2.
But Doctor,
So
340 you get it from where?
It's quite confusing on my notes here. Okay, never mind. I will discuss the one on the offline lecture later on.
Okay.
Okay, we proceed with the notes first. We shall keep this example because I need to check again my notes here.
Okay.
Example and tutorial I will skip. It will take some time. So we proceed on the page 15, control halfway rectifier, because we have another half an hour to go. Okay. Because we have to take note, differentiate between input and output. The given here is the input voltage, and the 240 volt is the input voltage RMS. Okay, I discussed in the pre-recorded letter on that exercise and tutorial. So proceed to page 15. Sorry. I think the tutorial here, the most of the answer is correct. You try first. I'll check and upload the discussion later on the Google Classroom. Okay, now proceed with 15, page 15 first. Okay, as I mentioned to you, when we have this kind of device which have a
switch
marking on the cathode side, so it's so called a control device. Okay, wait. So this is so-called gate. If we have diode or power device, it have included the marking here. So this is the gate actually. So what we use for this part is to induce signal to the power switch or the diode here. So it's no more called diode lah. It's a silicon control rectifier. And silicon or signal control rectifier lah. Thyristor, or the short name will be thyristor, which is used to control the output of the rectifier. So the SCR only we conduct when the source become positive, but the conduction is delayed until the gate signal applied. And so means that if you put a positive bias throughout your device here, so during positive cycle, what happens that you have a positive bias. Okay, but this device will not conduct until you put signal onto the gate. You put a pulse, and you put a pulse. Some device is controlled by current, some device controlled by voltage. Let's say you put a current pulses. Put a current pulses, certain milliampere to the gate. So only at this time, let's say this is your alpha. After zero, draw here. After positive cycles, certain times, only you apply alpha. And you apply your signal, alpha here. Then only the device will conduct. And you have positive cycle of input, but you apply alpha at this point. At this point you apply, only you can see that the output is appear at your load. And this is your input. This is the point of your alpha. So this is your output that you can see from your load from here. If you take a look from here, or you probe it from here, so this is your output waveform. Okay, it will trigger during alpha, but it will switch off once the cycle enter negative portion. Positive cycles, negative cycles. Means that during positive cycle, it conducts after alpha, but when the circuit moving into negative cycles, so you stop lah. It behave like diode. Positive cycles behave like SCR, negative cycle just behave like diode. So it will not conduct during or under negative cycles. Okay, so that's the behavior of SCR, silicon control or signal control rectifier. Okay, any question? So you provide some sort of gate controls circuit to apply or to produce IG, current for the gate to operate. So in our simulation, in PSIM, the gate control or signal is just generated by the signal generator, simple signal generator. But in real life, you have to compose a circuit in terms of how to supply this gate to operate. So it depends. Different SCR, they have different voltage rating, they have different current rating, and they have different current range value for your gate. And the controlling gate, they need different kind of current value. So it's up to the requirement of the circuit and the requirement of the device. So you yourself have to determine. And so in your later parts or in future discussion, we shall see in terms of how much the voltage need to be generated here, how much the current you need for your load. So it will depend. It will be the parameters for you all to select what kind of switch here and what kind of switch, power rating, current rating, voltage rating of the switch to be selected on your or to be applied to your system, and how you want to what kind of control or signal, current intensity, voltage rating that you need to compose for your circuit or for your device. And it depends also on the rating or range of your source. So 3 parts that you have to consider. I think 4 lah, but this one is not so much be impressed on. But these 3 parts need to be considered on this power processor or power processing consideration. Okay, if you can see from this slide, it shows here the input of your signal. V source here have full cycles, but what you can see from resistive point of view, the load, it just conduct during alpha and off on the negative cycle, and repeats again on the another alpha. Means that each cycle you have to pass the alpha, and you have to put the alpha here, alpha 1, alpha 2, alpha 3. So each cycle you have to induce or you have to produce the signal into the gate. And so now it depends on the cycles, and how much the cycle. If 60 Hz, so the duration follows 60 Hz cycles. If 50 Hz, so 50 Hz. If more than that, kilohertz, so the signal also be in kilohertz cycles. So in terms of when you measure or you probe at the device itself, so this is the signal that you can see lah. When it blocks, it has voltage and go to 0. When it blocks, it has voltage go to 0, and it has tails here because this part it blocks the voltage. So the half-wave control rectifier output is given by this one. V out is normal Vm over 2 pi, but you have to plus the amount of 1 plus cos alpha. And you have to determine how much the alpha. So the higher the alpha, it means that the lower the V out. You can see lower the alpha, you will have higher V out. But when you increase the alpha, so the output average voltage will be reduced. And the higher the alpha, the lower the V out. In terms of average power absorbed by the resistor, also the same, V square over R. V out here, this is V out, VRMS out, divided by R, or I square R. I is the amount of your absorbed current RMS to the load times the value of resistive amount. And your VRMS is equal to VM divided by 2 times 1 minus alpha divided by pi sine 2 alpha divided by 2 pi. And actually all the iteration here will be done, and I'll share with you all the PE curve that we generate for you all to refer. How much actually the output in terms of voltage, RMS, average, be out. Because we are not focusing on how you want to remember and calculate, and we need you all to appreciate in terms of if you shift to certain point, what you expect to happen, and the value we can just probe from the graph that we will share. I should share before, but I forgot. I will share later on the PE curve. So this is an example I discuss later in this one. So now we have come to the conclusion. You have learned about uncontrolled half-wave rectifier and also controlled half-wave rectifier with resistive load. Okay, any question from the floor? Ada sebarang soalan? I'm searching for the graph that I should share with you. So this afternoon session will be labs. Lab hour. We start at 12. So I will attend on the first 10 or 15 minutes, give you a briefing, and I will leave you all to the labs. Okay, wait, I want to show you all the graph.